Okay, so now we're going to look at titration curves with the knowledge that we know about buffers. So let's first look at a strong acid, strong base. So this is not an example of a solution that can buffer the addition of the strong acid or strong base. So here I have my strong acid HCl. So we know, if we look at the graph, we know that we're starting with HCl because the starting pH is low. So in my solution here, I have the chlorine ions and the hydronium because it's a strong acid, so a strong acid is going to completely dissociate in solution. Okay, so now I'm titrating with sodium hydroxide. So I'm adding sodium hydroxide to the solution, which is also a strong base, so it's also going to dissociate into sodium ions and hydroxide ions. So I'm going to add my sodium ions. They will just float around in solution, not reacting with anything. But the hydronium is going to react with the H plus ions in solution to form water. And so in my diagram, I'm not going to draw the water molecules, but if you look, if I add them here, they could be here. Okay, so now in my solution, I'm going to have the same thing. My chlorine ions are still going to be there. Now I have sodium as well, and I now only have the one H plus ion. Okay, so that's what you can see here in the graph, the slight change of pH. Okay, and just keep in mind that in a titration, we're breaking it down so that it's particle by particle, but we're really simplifying it. So you're going to be adding hydroxide, or you're going to be adding sodium hydroxide in large amounts, so in larger amounts than just one particle at a time. So this is just a very slow representation of what's happening rather fast. Okay, so next I'm going to again add my same thing to solution, and the same reaction is going to happen. So now in solution I just have the ions floating around. So I'm going to still have my two chlorine ions, and now I'm going to have two sodium ions. The hydroxide is going to completely react and neutralize the H plus ion. So I'm going to now have more water and no hydroxide or H plus ions at all in solution. So at this point, we're at our equivalence point, which means that the solution, all of the acid has reacted with the base. And as you can see in the particle diagram, there are no ions in solution that are going to be changing the pH. It's just the water, and water is neutral. So the pH at our equivalence point is going to be 7. Because it's a neutral solution. Okay, so make sure you just understand that for a strong acid base, the pH at the equivalence point is 7. Because the solution has completely neutralized. There is no longer any H plus ions in solution. It's all been reacted with hydroxide to form water molecules. Okay, but now I'm going to add more hydroxide, and then of course, as I add more hydroxide, now the pH is going to drastically increase, and that's where you get the new ending pH of between 12 and 14, so representing a strong base. Okay, so my particle diagram is going to now no longer fit into this little tiny box, but you get the idea. And then it would just continue to do that as I add more strong base. Okay, so pretty simple, straightforward. Now we're going to look at weak acid, strong base, and our ideas of the buffer are going to come into play here. Okay, so I have a weak acid, acetic acid, in solution. I know it's weak because if I look at the graph here, I can see the pH, starting pH is around 3, 4-ish, a high 3, almost 4. Okay, so that's indicating this is a weak acid. I can also look at the titration curve and see that the pH at the equivalence point is slightly higher than 7. Okay, and so we're going to get into why that is. And you can also see this region right here has a little bit of a curve as opposed to this straight line as you saw in the strong acid, strong base. And so we call this region the buffer region. Because at this point, my weak acid reacts with the added strong base to neutralize the solution. So I don't see such a stark change in the pH. It can kind of resist the addition of the strong base by forming the conjugate base. Okay, so let's just do our particle diagram. So I have 2 particles of the CH3COOH, and now I'm adding my sodium hydroxide. So the hydroxide ion is going to react with the acetic acid, just like how we saw in the buffer solutions, and it's now going to form, so I'll still have the one, okay, I'll still have one molecule of my acetic acid remaining that has not reacted, but now I'm going to have an additional, now my conjugate base has been formed, and water. Okay, and the sodium ion is just floating around in solution. Okay, so we call this the half equivalence point because the concentration of the weak acid and its conjugate base are equal. So at the half equivalence point, you can see I have 1 particle of my weak acid and 1 particle of my weak base. So concentration of weak acid and weak base are equal at the half equivalence point. Okay, and that looks like on my graph, so here on this curve in the middle here, my weak acid and its conjugate base are equal to each other. Okay, sorry, my other video got interrupted and I decided to add something else to this video. So we left off talking about the half equivalence point where the concentration of my weak acid and conjugate base are equal to each other. And we know the Henderson-Hasselbalch equation can give us a clue as to what the pH and the pKa are during this moment in the titration. So my pH, according to the Henderson-Hasselbalch equation, pH equals pKa plus log of the concentration of the base over the acid. Okay, so at the half equivalence point, this is going to be 1 because they're equal concentrations. And then the log of 1 is just 0, so I can just completely disregard this. And now that tells me that the pH and the pKa are equal to each other. So that's around this point in the titration, the midpoint of this first curve. And at that point, the pKa equals the pH. And you can see that in the diagram above where I have 2 weak acids and 2 conjugate base particles. So the other part that I want you to note is that up until the half equivalence point, my concentration of the weak acid is going to be greater than the concentration of the weak base. So if I look at the particle diagram, I have 3 weak acids that are still present in solution versus only 1 conjugate base. After the half equivalence point, now I have 3 base particles and only 1 weak acid. So that tells me after the half equivalence point, my concentration of the weak base is going to be greater than the concentration of the weak acid that I initially started with. Okay, so then after I add sodium hydroxide again to this solution that I see, I'm now going to have all of my weak acid reacting with the hydroxide. So now my solution is going to look like only conjugate base is present. All the weak acid has reacted. And this is the equivalence point. So in any titration, the equivalence point is the point in the reaction when all of the acid or base has reacted with the whatever it was being titrated with. Okay, so if you notice on the graph, you'll see that the pH at this point is a little bit greater than 7. Okay, so at the equivalence point for a weak acid strong base titration, the pH is greater than 7. Okay, that's interesting. That's not because we're titrating with a strong base and the strong base is really strong, so it's going to be greater than 7. Because if I looked at the titration above, I had a strong base that I was titrating with, but the pH was 7 at the equivalence point. So it's not about the thing that's titrating that you're using to titrate. It's this reaction that happens between the conjugate base and water in solution. So if I'm looking at my conjugate base plus water, that's going to yield, again, a little bit of weak acid and OH. Okay, so this is what's going to cause that increase in pH at the equivalence point in a titration with a weak acid and strong base. So it's because the conjugate base is going to react to form some hydroxide, thus raising the pH at the equivalence point. Okay, and then if I just keep adding sodium hydroxide, it's going to continue then at this point to form more OH, and that's going to drive the pH to have this sharp increase, and then that tells us that the titration is complete.